Hi viewers, welcome to my class on mechanics of materials. In today's class, I will discuss numerical examples on thermal stresses induced in composite bars. Now let us work out a numerical example. A composite bar consists of a steel rod 25 mm diameter within a copper tube 35 mm outer diameter and 25 mm inner diameter. Find the stresses induced in the composite bar when the temperature of the assembly rises through 35 degrees centigrade. ES is, that is Young's modulus of steel, is 200 gigapascal and alpha is 12.6 into 10 raised to minus 6 per degree centigrade. EC, Young's modulus of copper, 100 gigapascal and alpha C 18 into 10 raised to minus 6 per degree centigrade. So we have a steel rod and it is inside a copper tube which is having same inside diameter same as the diameter of the steel rod and outer diameter 35 mm. Now the temperature of the assembly is rising through 35 degrees centigrade. So delta T is 35 degrees centigrade. Young's modulus of both the materials are given and coefficient of linear expansion is also given for both the materials. So this is assembly like steel rod which is having 25 mm diameter, whereas copper tube is outside the steel rod. Okay, or steel rod is inside the copper tube. So copper tube is having inside diameter 25 mm and outer diameter 35 mm. So they are rigidly connected, bonded together, so that no individual expansion or contraction is allowed when the temperature changes. So it can be taken as a composite assembly. Now you can find out the area of cross section of steel pi by 4 into d square, where d is the diameter of the steel rod. So diameter is 25. So pi by 4 into 25 square, you get 490.874 mm square. Okay, and the unit is mm square. Now area of cross section of copper is pi by 4 into d naught square minus di square. So you will get pi by 4 into d naught, outer diameter is 35, inside diameter is 25. So 35 square minus 25 square, you get 471.239 mm square. Once again, unit is mm square. So the areas are almost equal, not exactly equal, but they are very close, and since the areas are almost close, the stress also will be almost nearer. Okay, if they are equal, stresses will be equal. Equal means magnitudes are equal, numerical values are equal, but they are opposite stresses. In this case, copper is having higher coefficient of linear expansion and steel is having less coefficient of linear expansion. Since we are heating it, copper will try to expand more than steel and copper will be subjected to compressive stress, whereas steel will be subjected to tensile stress. Copper is trying to expand more, steel is expanding less, so steel will exert a compressive force on copper, preventing its free expansion. In turn, copper has to pull steel along with it beyond the steel's natural expansion. So tensile force in steel, compressive force in copper. Now sigma SAS is equal to sigma CAC, that is the first relation, and sigma S is AC by AS into sigma C. Area ratio you can take, you get area ratios. AC is 471.239 and AS is 490.874. If you take that ratio, you will get 0.9599, and so sigma S is 0.9599 sigma C. So stress induced in steel is less than stress induced in copper. Now you have the second relation, sigma S by ES plus sigma C by EC is equal to, here you should take that higher coefficient of linear expansion first, Okay, alpha C, copper is having higher coefficient of linear expansion. So alpha C minus alpha S into delta T. Now sigma S we know in terms of sigma C that I have substituted. ES is 200 into 10 raised to 3, 200 gigapascal, so 200 into 10 raised to 3, and sigma C. EC is 100 into 10 raised to 3, 100 gigapascal. For copper 100 gigapascal, so 100 into 10 raised to 3. Alpha C is 18 into 10 raised to minus 6, and alpha S is 12 into 10 raised to minus 6. Delta T is 35. So solving for sigma C, you can, left hand side it reduces to 1.47995 sigma C is equal to here 35 into this reduces to 0.54. So you'll get sigma C as 12.77 Newton per mm square, and that stress is going to be compressive because copper is trying to expand more, so steel will exert a compressive force. Now once you get the stress in copper, you can find out the stress in steel by multiplying with that area ratio, which all relationship you already got it. So sigma S is 0.9599 sigma C, or this into 0.9599 will get 12.26 Newton per mm square, and this is going to be tensile stress. So the material with the higher value of coefficient of expansion in a composite bar is subjected to compressive stress when heated, and the other material will be subjected to tensile stress. Now let us work out another example. A composite bar is made of central steel plate 60 mm wide and 10 mm thick, to which copper plates of 40 mm wide and 5 mm thick are connected rigidly on each side. The length of the bar at normal temperatures is 1 meter. If the temperature is raised by 80 degrees centigrade, determine the stresses in each metal and change in length. ES value is 200 giganewton per meter square, EC is 100 giganewton per meter square, alpha S is 12 into 10 raised to minus 6 per degree centigrade, alpha C is 17 into 10 raised to minus 6 per degree centigrade. So that's a steel plate 60 mm wide and 10 mm thick, and to this steel plate copper plates of 40 mm wide and 5 mm thick are connected on either side. So there are two copper plates, top and bottom of the steel plate. The length of the bar at normal temperature is 1 meter. So you have 1 meter length for the bar, and the temperature is again here it's raised by 80 degrees centigrade. So the property Young's modulus and alpha for both materials are given. Now let us see. So this is the steel plate, which is 60 mm wide and 1 meter long, and thickness is 10 mm, and on top of that you have a copper plate which is 40 mm wide and the same length and 5 mm thick. And bottom also you have similar copper plate, so they are rigidly bonded, so no individual expansion or contraction is permitted since they are connected rigidly. Now when the temperature is rising, copper will try to expand more, and that will not be allowed by steel, and compressive stress will be induced in copper, and steel in turn tensile stress will be induced. Now width of the steel plate is 60 mm, thickness of steel plate is 10 mm, width of copper plate is 40 mm, thickness of copper plate is 5 mm, length of the assembly is 1 meter or 1000 mm. Delta T temperature change is 80 degrees centigrade. These are the Young's modulus of both the materials. Giganewton per meter square is gigapascal only. 200 into 10 raised to 3 Newton per mm square. This is 100 into 10 raised to 3 Newton per mm square. Alpha S 12 into 10 raised to minus 6 per degree centigrade. Alpha C 17 into 10 raised to minus 6 per degree centigrade. And we have first relation connecting the stresses, and they are related by area ratio. So you have that first relation, force in steel is equal to force in copper. So here both are of opposite nature. Copper is subjected to compressive stress and steel is subjected to tensile stress. Now let us calculate the area of steel and copper. So steel is having a width of 60 mm and thickness 10 mm. So 60 into 10, 600 mm square. That is the cross section area of steel. And copper, it is having 40 mm width and 5 mm thick. So it's 40 into 5, and again another strip is there, 40 into 5. So 40 into 5 into 2, that is 400 mm square is area of cross section of copper. Now we can use sigma S is equal to AC by AS into sigma C. AC by AS into sigma C. AC is 400, AS is 600. So 400 by 600, you get 0.667 sigma C. So stress in steel is 0.667 times stress in copper. So steel is subjected to less stress because area of steel is more compared to the copper. So steel will be subjected to less amount of stress. Now second relation is sigma S by ES plus sigma C by EC is equal to alpha C minus alpha S into delta T. Higher coefficient of linear expansion you should write first. So here copper is having higher coefficient of linear expansion. Now sigma S we already got 0.667 sigma C, and ES is 200 into 10 raised to 3. Sigma C by 100 into 10 raised to 3. Alpha C 17 into 10 raised to minus 6. And alpha S is 12 into 10 raised to minus 6, and temperature change is 80. So if you work out this, you get sigma C as 29.99 Newton per mm square, and we know that copper is subjected to compressive stress. And sigma S is 0.667 sigma C. So you multiply this with the 29.99, so you get 20.007 Newton per mm square tensile stress. So steel is subjected to tensile stress of this magnitude, and copper is subjected to compressive stress of 29.99 Newton per mm square. Now the change in length of copper bar or steel bar, both will be same. You can find out the change in length in copper bar as alpha C L C delta T, that is free expansion of copper, and free expansion is not allowed. Compressive stress induced in that is reducing this expansion by this amount. This is a change in length in copper bar due to the compressive stress induced. So this is free expansion minus change in length due to compressive stress induced, that will give the expansion of the composite bar. When they are in a composite bar, so much expansion is only allowed. This is a free expansion, and this is a reduction in expansion due to compressive stress. So alpha C is 17 into 10 raised to minus 6 into a length of the bar. LC and LS are same, 1000, and delta T is 80 minus sigma C we already got 29.99 divided by 100 into 10 raised to 3 into 1000, which will work out to 1.0601 mm. The change in length in steel bar, if you calculate also, you will get the same value, because steel is also subjected to the same change in length. But in steel, the free expansion is alpha S ELS delta T, and steel is pulled beyond its natural expansion. So you can use that value, natural expansion, that is alpha S LS delta T plus sigma S by ES into LC. That will give the same value, and because both materials are changing its length by the same amount, both the materials will expand by the same amount. That's all for today. Thank you for watching.